Codemasters 2016 solution for question 6. I'm Andrew Turpin from the University of Melbourne. So question 6 is the toughest one of the lot by far and requires some really tricky algorithmics to solve all parts. So it's a road trip. We're going from petrol station to petrol station, and maybe it looks something like this. So we're given petrol stations, and we're also given the number of litres of petrol required to travel between the two petrol stations. So this is the first example. If we ignore these, we've got 3 petrol stations, 1, 2 and 3. 1, 2, 3. And we have to get to the 3rd petrol station and our journey's over. We've got 40 litres in our tank. So we know that we could make this journey. We can go 15, plus 15 is 30, plus 10 is 40. So we can make it all the way to the end without filling up, and that's great. But of course, if we look at the second example, we've got 25, 25, 10. So we've got 25, 25, 10. Now in this case, of course, we can't make it all the way to the end without filling up. So we have a choice. We can either fill up here, in which case we can make it to the end, 35. And that's our only choice, because we can't make it here without filling up. So we have to fill up here, and the amount of petrol is going, we've used 25 to get here, so we're going to have 15 litres left in the tank. So we're going to have to buy 25 litres of petrol at the price of petrol station 1, and then we can make it all the way to the end. So we have to buy 25 times 1.2, 25 times 1.21, which is 30.25 for the cost. So in general, these files get longer and longer, and it's harder and harder to work this out in your head. General, if we have n nodes here, so we've got 1, 2, 3, all the way up to n, then at each one we have a choice. We can either fill up or we can not fill up. And so if we didn't, we could represent this as a binary string of n bits. So at the first petrol station, we don't fill up. Second petrol station, we don't fill up, don't fill up, don't fill up, don't fill up, all the way to the end. So if we don't fill up anywhere, we'd have that binary string. Or we could not fill up anywhere except for the second last petrol station. Or we could not fill up anywhere except for the third last petrol station. And so on. These are supposed to line up. Thanks, PowerPoint. So we could keep going like this and look at all the possible combinations of petrol we could buy until eventually we get down to 1, where we buy petrol at every possible petrol station. So looking at this, we can see that there are 2 to the power of n possible ways of buying petrol. 2 to the n possible combinations of petrol buying and petrol station. So this is a classic combinatorial problem from computer science, where you're faced with a search space of 2 to the n possible choices, and how do we go about finding which one gives us the lowest price of petrol. Some of these won't be feasible as well, right? So this one, for example, where we only fill up at the second last petrol station, wouldn't work for all cases. So not all of them are feasible, and of the ones that are feasible, what's the lowest cost? The simplest way to represent this in a coding scenario is with a recursive program. So we can define a function, let's just call it cost. Which station are we at? And how much petrol do we have left? Petrol left equals what? So we've got a choice. We can either buy petrol at this station. So if we buy petrol at this station, we've got 40 litres minus the amount of petrol we've got left, multiplied by the price at this station, plus then, so we buy petrol at this station, and then we keep going from the next station along with 40 litres in the tank. So that's what happens if we fill up at this station. If we don't fill up at this station, what can we do? Well, it doesn't cost us anything, so we don't need any of this. And we keep going at the next station, but we will have used however much it required. So required. So what have we got here? We've got price I is the cost of petrol at station I, and we've got required I is the number of litres of petrol to get from I minus 1 to I. So if we buy petrol here, we have to buy this much at this price, and then we're moving on to station 1. Actually, when we get to station 1, we'll have already used the petrol to get there. Let me make this a bit broader. So if we purchase petrol, we pay this much, and then we keep going. If we don't purchase petrol, then we just keep going. So if you like, it's 0 plus. And we've got to take the minimum of these two things. The minimum of either buying petrol or not buying petrol. And that will give us, and what we're looking for in the end is the cost to get to the final station. That's not correct. The cost to start from station 1 using, so this is the answer we're looking for, right? So this expression here is going to give us the cost, the minimum cost to get from station to the end. So cost ij gives the minimum cost to get to station n from I when tank has j litres. So a simple recursive equation taking the minimum of the two choices. Either we buy petrol here or we don't buy petrol. And this is the answer we want, beginning at station 1 after we've already used the amount of petrol required to get to station 1. So this is a fairly high level. There's still a bit of work to do to turn this into some code. So for all recursive functions, we also need a base case. So the cost to get from station n with any amount of petrol is 0. Yep. So if we get to station n with some petrol left, then there's no cost and we're finished. So that's the base case of the recursion. Still quite a bit of work to do. This doesn't at all take into account feasibility. What happens if 40 minus petrol left is in fact negative, or 40 minus required station is negative? What if you don't have enough petrol to reach the next station? So you have to be careful about that as well. How do we turn it into code? Well, it's almost code. We just need a few bells and whistles. So we could do something like this if we're using Python. We can turn it into a function. Let's take the first part. So if we fill up, it's going to cost us this. And if we don't fill up, it's going to cost us this. Where are we? We need a base case. So if station equals n, if petrol left, oh well, if station equals n, we're done. Return 0, there's no cost. If we're making a valid code, I better put that in. What about this feasibility thing? What happens if we get to station, we're up to here and the petrol is negative? So if the petrol left is less than 0, then this is not a feasible path. Return -1. So we could fill up with this, don't fill with this, and then we return the minimum of the two. And there you go. Now we just have to print cost of 140 minus require. And of course we also need to read in from the file the require array and the price array, which I haven't got here. So read in require and price from file. But again, if you're a seasoned competitive programmer, reading in stuff from file should be bread and butter. This still is not quite right. We're still going to run into trouble here, because what if this cost is -1? What if there's no way of going from station 1 onwards? So we need to just alter this a little bit. So, okay, well, temporarily fill equals this. And then if fill is greater than -1, then we can add on the cost of filling up. Otherwise, we leave it at -1. So that's almost working code. This won't quite work either, because if fill is -1 and don't fill is higher, yep, maybe that will work. I'll leave that there for now. So that's all very well and good, and that will work for parts 1, 2, 3, and 4 of the question. So it'll work for petrol 1, petrol 2, petrol 3, petrol 4, but petrol 5 has a lot of stations. And that means that this recursive function, the recursion will go very deep, and it just won't work. It's just too deep. So to answer the final question here, you have to transform this using a trick called dynamic programming, which you learn in second year university, or you can read about on Wikipedia. It's just a label of a technique for converting a recursive function, suitable recursive functions, of which this is one, into an array-based solution. And you can have a look at the code that I put up on the web, see how I did it. All right, thanks for listening.